Hello viewers, welcome back to the course on matrix computation and its application. So, today we are going to introduce the concept of similar matrices, that how we can define two matrices that are similar. So, let us do that. So, today we are going to discuss that suppose I have a transformation T from Rn to Rn. So, this is I am talking about the same space to the same space. Now, suppose I have a so first I want to see that how we can write the coordinates of a vector corresponding to different bases. For example, so let us write down, first I will take change of basis. Can be a basis or maybe suppose let I take R2. In the R2, suppose I have basis B1 that is given to me. So, I just take the very simple basis. So, let us take it is 1 0 and 1 1. So, this is the basis I am taking. So, let us call it U1 and call it U2. Now, I take the another basis B2. Suppose I take 1 minus 1 and 0 1, and I call this basis as V1 and V2. Now, we want to see that for any vector, maybe AB belongs to R2. So, for any vector I just choose any vector AB from R2, then how the coordinates of AB, then how the coordinates of AB are related. So, this one we want to discuss, because I can write the coordinates of, so let us this vector AB. So, I just take this vector as a column vector and I will write its coordinate with respect to B1. I will write the coordinates of same vector with respect to the basis B2, and I want to find what is the relation between these two. So, this is the relation I want to find. So, let us do this one. Now, so from here, so let I call this vector as a vector x. So, this vector is AB. And that belongs to R2. Now, from here I know that the vector x belongs to the basis B1. This one I want to write. So, suppose this is equal to maybe alpha and beta. From here I can write that I can write from here. So, x is my AB. So, my AB B1 is equal to alpha beta, which implies that my vector AB, this is my vector, is equal to alpha times. So, this is the basis I am taking. So, U1, so this will equal to U1 plus beta times u2, because this is what I am writing. And from here I can write from here that I take the matrix made up of u1 the first vector of the basis and u2 the second vector of the basis, and here I can write alpha beta. So, now from here I can say that, so this is my matrix corresponding to the basis B1. Okay, so I can, from here I can write that u1 u2 alpha beta, that is equal to AB, and AB is my x. So, let us call this matrix. So, I just have taken the basis B1. So, I just call this matrix maybe C1. So, C1 is the matrix made up of the basis, and from here one thing I know that this matrix C is invertible and is called change of basis matrix. So, this is called the change of basis matrix C. So, from here I can write this as the C1 and this is alpha beta. So, this is x with respect to the basis B1, I can write it as a B1, and that is equal to x. And from here I can write that B1 is equal to C1 inverse x. So, this is very easily we can write the basis, the coordinate of the x with respect to the basis, that is equal to the inverse of the matrix made up of basis into the element we are talking about. Similarly, we can write x of, so here I have taken the two bases B1 and B2. So, now I want to write with respect to basis B2 of the same element. So, this one I can write with the matrix. So, from here I can write that similarly I will make a matrix C2 which is a made up of the vectors V1 and V2 as a column vector. So, I call it V1 and V2, this is the column I have taken. So, this is also invertible, and from here we can write that C2 the coordinates of x with respect to the basis B2, that is equal to x. And now from here I can write that B2 is C2 inverse x. So, this is the, we are able to write like this one. Now, from here I can write, so I can call it equation number 1 and equation number 2. So, from 1 and 2, what I can write? I can write as x B1, it can be written as C1 inverse x, and this one can be written as C1 inverse, and x is like this one. So, from here I can write as C2 B2. So, that gives me that the coordinate of x with respect to B1 directly can be written as C1 inverse C2 with respect to B2, or, so this is the relation between the coordinates of the vector x with respect to basis B1 and with respect to basis B2, or I can write B2 is equal to C2 inverse, and x I can write from here C1 B1. So, this is the relation between the coordinates of the same vector with respect to different bases. So, let us verify this one. Now, let us verify. So, I take a element. So, let us choose a element, choose a vector x. So, I just choose the vector x as 3 2. So, let us choose this one, and I have the basis this one. Now, first I have to make the matrix C1. So, C1 is made up of this vector u1 u2. So, this is u1 u2, and this is what we are going to write here is 1 0 1 1. So, it is 1 0 1 1. So, this is my matrix C1. Now, I want to write. So, from here what I want to do, I want to write the. So, from here I know that C1 and x with respect to the basis B1, that is equal to x. Now, I want to find out what is the value of this one, the coordinate of this one, and from here I want to find B1, that is C1 inverse x. Now, C1 inverse will be, the determinant is 1 here. So, it will be swap, and this will be change of sign. So, this is my C1 inverse. So, I can write from here it is 1 minus 1 0 1, and x is 3 2. So, from here 3 minus 2 1, and it is 3 and 2. So, it is 1 2. So, now this is we are able to find. Also, I want to write C2. So, C2 I am writing with respect to the basis V1 and V2. So, C2 is basically V1 and V2. So, that is equal to the first one is 1 minus 1, 1 minus 1 0 1, and now my x with respect to B2 is C2 inverse x. Now, I can find my C2 inverse. So, this is 1. So, the determinant is 1, and then it is swapping and negative sign. So, it is 1 0. So, from here I can write that this is 1 0 1 1, and this is my 3 2. So, if you multiply this by, so it will be 3 and this will be 5. So, it is one is 3 5 and another is 1 2. So, this is the coordinates we are able to find. Now, we also know that with respect to, so this one we want to find. So, let us verify either of this one. So, maybe I can verify this one. So, x with respect to B2, this is equal to C2 inverse C1, C2 inverse C1, and then B1. So, let us do this one. So, C2 inverse is this 1 0 1 1, and C1 is 1 1 0 1, and x with respect to B1 is 1 2. So, let us see what is going to happen. Now, from here I can write as 1 0 1 1 and this one I multiply here. So, it is 1 plus 2 3 and this is 2 and now it is multiplied here. So, it is 3 and then it is 5 and from here also we have confirmed that this is my 3 5 and this is also coming 3 5. So, that is equal to x of B 2. So, this way we are able to find the relation between the coordinates of the same vector with respect to different bases, because once we are able to find the basis of one vector, coordinate of one vector with respect to one basis, then the coordinate of the same vector with respect to another basis, we can apply this formula and directly we can write that one. So, this is the relation between the change of basis matrix or the coordinate of the vector with respect to different bases. So, after this one we are going to introduce a very important concept. Now, suppose I have a transformation T from R n to R n and then we have the basis B 1. So, this is basis, suppose B the basis given to me, that is u 1, u 2, u 3, u n. So, now we have the transformation from R n to R n, then from here one thing is clear that the transformation matrix will be square. So, now we are talking about the square matrices. Now, from here I know that if I take any x, apply my T the transformation. So, what I do is that if I write the transformation and if I put the square around this, it means I am talking about the matrix corresponding matrix A. Now, from here I will get T x that is equal to A x. So, this is corresponding to the standard basis. Now, let we take a matrix C which is made up of u 1, u 2, u n. So, I put the first column as u 1, second column as u 2. So, this is the matrix and I know that C is invertible. This we know that this is a linearly independent. So, it is invertible square matrix. Now, from here I apply my C inverse to this x and I get the coordinate of this x with respect to the C. So, C is a change of basis matrix. So, I apply this one and I will get the coordinate of the same x with respect to the basis B. The same thing I apply here, C inverse, and I get from here the coordinate of T x with respect to B, and that can be written as again A x with respect to B. Now, from here I know that I can go directly from here by writing. So, now I am applying this one. So, I can apply my transformation T, the matrix with respect to basis, and this is the matrix we have previously we have represented by D. Let me check that how we have written So, here I am writing with the C matrix. So, let us check that one. Okay. So, because there also I am writing by C, so I should, but here I am writing with the this matrix C. So, let us write it D. So, now from here I can write that the T I am applying on B, that is equal to T x B, this one. So, this is what we are writing. So, this is the matrix D corresponding to the change of basis that we have done before, and we have represented by C. So, let us no problem, because C I am writing here. So, let us write this D. So, this is the way the transformation is taking place. Now, from here, now I know that T of x B with respect to the basis B. So, this T of x B is equal to D of x B, where D is the corresponding matrix, the matrix corresponding to the basis B. Now, also just in the from here we have written like this one, that coordinate of this one can be written in this form. So, I am using this concept here. Now, this x B I can write as C, and this is equal to x, where x is the vector corresponding to the standard basis, and from here I can write B is C inverse x. Now, I am using this concept here. So, now what I am going to do is that, so now let us see that what is the relation between D and A. So, we want to find, we are interested to find the relation between A and D, where my A is the transformation matrix So, this is the transformation matrix of T related to standard basis, and D is my transformation matrix of T related to basis B, the new basis I am writing here. And what is C? C is change of basis matrix. So, it is a matrix made up of the basis, whatever the basis it is given. So, now we want to find the relation between these two. Now, so from here I just write from here that I can write now D of x b. So, this is I am putting the D of x b, that is equal to T x, that is equal to T x b. And what is T x b? It is a vector in terms of b. So, that I can write as A x b, and this one I can write A x b, I can write as C inverse the element Ax, the vector Ax, and this one I can write as C inverse Ax. Now, the x I can write from here, I can write C inverse A. So, this x I can write as C B, because I know that with respect to basis C, this is equal to x. So, from here I am able to write that d of x b is equal to C inverse A C B, and this is true for any vector x with respect to the basis. So, it is true for all x belongs to the given space R n. Now, from here I can write that d is equal to C inverse A C, because this is true for all x belongs to R n, and now from here I can say that d is equal to this, and from which I can write that C d is equal to A C, and from here I can write that my C d C inverse is equal to A. So, in the both way I can write like this one, and now since C is invertible, then from here I will write down that, which implies that the matrices A and D are similar, because we know that the definition of a similar matrix. So, what is the definition? I just write the similar matrix, similar matrices. What is the definition? Suppose so we are talking about that the square matrix, the two matrices A and B. So, this is of the same order. Two matrices A and B are said to be similar if there exists a non-singular matrix P such that P of A is equal to BP, or so from here, so this is the definition of that P of A is equal to BP or P of B is equal to AP, no problem. So, from here I can write that, because P is invertible, so I can write from here that A will be equal to B. So, I can take inverse, so it will be P inverse BP, or from here I can write that P inverse that is equal to B. So, this is the definition of the similar matrices. So, if you see from here that now I can say that the matrix A and D are similar, and the matrix A is the transformation matrix corresponding to standard basis, and D is the transformation matrix corresponding to the new basis. So, that is the relation between these two matrices. Now, I will introduce the concept we have already seen, is that diagonalization. Of a matrix. So, this diagonalization of the matrix we have seen from the matrix theory, that suppose I have a matrix A that is n cross n that is given to me. I was talking about the real matrix. Now, from here A we go to the matrix. Now, from here I know the concept of eigenvalues. So, this is already we have introduced from the matrix theory from my previous knowledge, that suppose I have a matrix A and then I have its eigenvalues. So, eigenvalue we generally write by A x is equal to lambda x, and from there I will find out the eigenvalue, and from here x, this is called the eigenvector. So, that is there. Then from here if I have a n cross n matrix, then suppose A has eigenvalues lambda 1, lambda 2 to lambda n. So, it can have a n number of eigenvalues, and suppose I consider that these eigenvalues lambda i's are real. So, that we are considering that suppose this is a real eigenvalue, we are not talking about the complex, and then we take the corresponding eigenvectors. So, corresponding eigenvector I am writing as, so this is a x. So, I can maybe instead of x I can represent by A u is equal to lambda u, because we are writing the vectors maybe in the terms of this one. So, the same thing, eigenvalue and eigenvector. Now, I take the corresponding eigenvectors. So, suppose we are able to write the eigenvectors u1, u2, un, and we are able to get this n number of eigenvectors. So, n number of eigenvectors we are able to get, and corresponding eigenvectors are this one and are linearly independent. So, I know that if this eigenvalue are distinct, then definitely these eigenvectors will be linearly independent, but since suppose that some eigenvalue is repeating, then still we are able to find the vector which are linearly independent. So, that is there. So, now if we are able to get the, so I take the basis now B as this vector eigenvectors, n number of eigenvector I will get, and I take this is a set of bases, because this is a linearly independent any number. So, it is a basis of R n. Now, from here I will write that now. So, we know that the matrix A is, so in this case is said to be similar to a diagonal matrix, we call it D. Then whether the matrix A is said to be similar to the diagonal matrix D if there exists a non-singular matrix P such that, now from here you can write down, because by the definition we have written this one, that P A is equal to B P. So, from here I will write that A of P is equal to P of D, and from here I know that this is equal to, I can be written as A can be written as P D P inverse or P inverse A P, that is equal to D, and this matrix P. So, now from here I should write that the matrix P is made up of this vector as column vector u1, u2, un. So, this is my corresponding invertible matrix we are writing, and D is the diagonal matrix, and it is made up of the diagonal elements, the eigenvalues as a diagonal elements. So, it is equal to lambda 1, lambda 2, lambda n. So, what we have done here is that now we have started with any matrix, and then corresponding to this matrix we have calculated the eigenvalues and the corresponding eigenvectors, and from here we are able to get n number of linearly independent eigenvectors. So, I have constructed using this eigenvectors a matrix P which is invertible, and then from the concept of similar matrix, what we have done here, we have showed that this matrix A is similar to the matrix T. So, how I can find the matrix P? So, P is the matrix is made up of eigenvectors. Now, from this we are able to see that this P inverse A P is equal to D. So, from here I can say that this matrix are similar, and also similar matrices have same set of eigenvalues. So, they have a same set of eigenvalues, that is the property of the similar matrix, because I am able to write A P is equal to P D. So, A is equal to P D P inverse, that is A can be written as equal to P inverse, sorry, D. So, it is the earlier we have done this concept in the course of matrix theory, but there we have not seen that what is the meaning of this A and D in the terms of linear transformation, but now we are able to see that we are writing the same matrix A in the different bases, and the bases are coming as the eigenvectors, and then we are able to show that we are finding the new matrix, transformation matrix D, that is made up of the eigenvectors. So, this way we are able to convert this one, and now we can see that the matrix A, suppose somebody wants to ask me that what is the value of A 5, then maybe I can use this formula. So, I can write my P. So, suppose I want to find A square. So, it is P D P inverse and then P D P inverse. So, this can be written as P D P inverse P then D P inverse, and this is my equal to the identity matrix. So, I can write P and D is the diagonal element D square. So, it will be D square P inverse. So, the same way I can write that my A n will be P D raised to power n P inverse. So, by doing this transformation we can easily handle such type of things very easily, because I want to find A n, just I will write the D raised to power n, and that is a diagonal elements diagonal matrix. So, it will be just the raise n to all these eigenvalues, and that will be the solution of this form. So, we are generally doing this transformation to make the life simpler, to deal with the corresponding the transformation matrix of the linear transformation. So, this is the use of the change of basis for the given linear transformation. So, this is a way we are defining this one. So, let me stop here today. So, in this lecture we have discussed a very important concept, that is the similar matrices, that how the change of basis of the corresponding transformation are used to introduce the two different type of matrices, that is we call it the similar matrices, and this concept is useful for using for satisfying the other properties of the given matrix, or to deal with the properties of the other matrices. So, I hope that you have enjoyed this lecture. Thanks for watching. Thanks very much.